Yes, it is correct that the transformer is considered a separately derived system. The secondary side of the transformer must be bonded and grounded, and the grounding electrode conductor size would be determined based on the secondary conductor size according to National Electrical Code Section 250.66. Regarding disconnecting means, yes, it is correct that a disconnecting means is required on the primary side of the transformer, sized at 125% of the transformer primary current rating. According to National Electrical Code Table 450.3, secondary overcurrent protection is not required if the primary overcurrent protection is rated at 125% of the transformer's primary current rating. However, the National Electrical Code does not explicitly address the requirement for a disconnecting means on the secondary side of a transformer that powers machinery. In general, it is good practice to provide disconnecting means for all electrical equipment, including transformers. In this case, since the transformer is remotely located from the machine and there is a disconnect at the machine, it would be appropriate to provide a disconnecting means on the secondary side of the transformer as well. This would allow for isolation of the transformer and provide a safe means of servicing or replacing the equipment. Now let's delve deeper into each aspect, starting with grounding. When dealing with a separately derived system like a transformer, establishing a proper ground is paramount for safety and proper operation. Firstly, the concept of a separately derived system means that the transformer creates a new electrical system independent of the source. This independence necessitates establishing a new ground reference. The grounding electrode conductor, often referred to as the GEC, connects the transformer's grounded conductor, typically the neutral, to a grounding electrode. This electrode can be a metal underground water pipe, the building steel if effectively grounded, or other approved electrodes as outlined in the National Electrical Code. The size of the grounded electrode conductor is crucial. As previously stated, National Electrical Code Section 250.66 dictates the sizing based on the size of the secondary conductors. To accurately size the GEC, firstly, determine the size of the secondary conductors. Secondly, consult National Electrical Code Table 250.66. This table correlates conductor size with the required GEC size. Remember that the table specifies minimum sizes, and local codes or engineering practices might require larger conductors. Proper bonding is equally critical. Bonding ensures that all metallic parts of the electrical system are at the same electrical potential. This includes the transformer enclosure, metal conduit, and other non-current carrying metal parts. The bonding conductor connects these parts to the grounded conductor, providing a low impedance path for fault current to flow back to the source, facilitating the operation of overcurrent protective devices like circuit breakers or fuses. Now let's shift our focus to disconnecting means. Disconnecting means are switches or circuit breakers that allow for the complete isolation of electrical equipment from the power source. This is essential for safe maintenance, repair, and troubleshooting. The primary disconnecting means, located on the input side of the transformer, should be readily accessible and clearly labeled. Its purpose is to de-energize the entire transformer. As noted earlier, the primary overcurrent protection is often sized at 125% of the transformer's primary current rating. This sizing is based on National Electrical Code Table 450.3, which permits this higher rating under specific conditions, mainly to accommodate inrush current during transformer energization. Inrush current is a brief surge of current that occurs when a transformer is initially energized. It can be several times higher than the normal operating current. Sizing the overcurrent protection at 125% helps prevent nuisance tripping caused by this inrush current. The question of a secondary disconnecting means is more nuanced. While the National Electrical Code doesn't explicitly mandate it for transformers powering machinery, providing one is generally considered a best practice. The rationale behind this recommendation is twofold. Firstly, it provides an additional layer of safety for personnel working on the machinery or the transformer itself. Isolating the secondary side allows for safe troubleshooting and repair without the risk of backfeed from the primary side. Secondly, it simplifies maintenance and replacement. If the transformer needs to be serviced or replaced, a secondary disconnect allows for quick and easy isolation without affecting other equipment connected to the primary side. When considering the location of the secondary disconnecting means, several factors come into play. Since the transformer is remotely located from the machine, having a disconnect both at the machine and at the transformer is advantageous. The disconnect at the machine provides a local means of isolation for machine maintenance. The disconnect at the transformer provides a central point for isolating the entire transformer circuit. The type of disconnecting means can vary depending on the application and local codes. Common options include fused disconnect switches and circuit breakers. The disconnecting means must be properly rated for the voltage and current it will be carrying. It should also be readily accessible and clearly labeled. In summary, grounding and disconnecting means are critical aspects of transformer installations. Proper grounding ensures safety and proper operation. Disconnecting means provide a means of isolating the equipment for maintenance and repair. While the National Electrical Code provides specific guidelines, it's important to consider best practices and local codes to ensure a safe and reliable installation. Here is a more detailed breakdown of grounding electrode conductor sizing based on National Electrical Code Section 250.66. The grounding electrode conductor connects the separately derived system's grounded conductor to the grounding electrode. Its purpose is to provide a lower impedance path for fault current, facilitating the operation of overcurrent protective devices and minimizing voltage rise during ground faults. National Electrical Code Section 250.66 provides specific rules for sizing the grounding electrode conductor based on the size of the derived phase conductors. Firstly, determine the size of the largest ungrounded conductor of the derived phase conductors. This is usually determined by the load calculation for the equipment served by the transformer. Secondly, once the size of the largest ungrounded conductor is known, refer to National Electrical Code Table 250.66 to determine the minimum size of the grounding electrode conductor. National Electrical Code Table 250.66 provides a correlation between the size of the ungrounded conductors and the required size of the grounding electrode conductor. The table specifies minimum sizes for copper, aluminum, and copper-clad aluminum conductors. Thirdly, consider the material of the grounding electrode conductor. National Electrical Code Table 250.66 provides different conductor sizes for copper, aluminum, and copper-clad aluminum. Select the appropriate column in the table based on the material of the grounding electrode conductor being used. Fourthly, consider any applicable exceptions or modifications to National Electrical Code Section 250.66. There are certain exceptions and modifications to the general rules for sizing grounding electrode conductors, depending on the specific application and type of grounding electrode being used. For example, if the grounding electrode is a concrete encased electrode, certain rules apply. The general rule is that the grounding electrode conductor cannot be smaller than #8 copper. Another common grounding electrode is a ground ring, and the grounding electrode conductor is sized to the derived phase conductors. The final step is to install the grounding electrode conductor in accordance with National Electrical Code requirements. The grounding electrode conductor must be installed in a manner that provides a permanent and effective ground path. It should be protected from physical damage and securely connected to the grounding electrode and the grounded conductor of the separately derived system. Keep in mind that the aforementioned is a general overview of the grounding electrode conductor sizing process according to National Electrical Code Section 250.66. It is important to consult the latest edition of the National Electrical Code and any applicable local codes and regulations to ensure compliance with all requirements. In addition to grounding electrode conductor sizing, there are other important considerations for grounding separately derived systems, including bonding, ground fault protection, and coordination with overcurrent protective devices. Proper grounding is essential for ensuring the safety and reliability of electrical systems, and it is important to consult with a qualified electrical professional to ensure that all applicable requirements are met. Now, let's expand on the practical applications of disconnect sizing. In field, Accurately sizing disconnects is paramount for electrical safety and code compliance. This section provides a detailed guide on how to approach this task, ensuring that you select the right equipment for various scenarios. Firstly, understanding the basics is important. A disconnect is a device used to isolate an electrical circuit or piece of equipment from its power source. This isolation is critical for safe maintenance, repairs, and in emergency situations. Disconnects can range from simple manually operated switches to sophisticated circuit breakers that offer both disconnection and overcurrent protection. Secondly, determining the load requirements for the disconnect is necessary. The first step in sizing a disconnect is to determine the maximum current that the circuit or equipment it will serve is expected to draw. This is known as the load current. This value is crucial because the disconnect must be rated to handle at least this amount of current continuously without overheating or failing. The nameplate of the equipment typically lists the full load amps, or FLA, which is a good starting point. For circuits with multiple loads, calculate the total current by summing the individual loads, taking into account any demand factors that might apply according to the National Electrical Code. Thirdly, applying the National Electrical Code guidelines is an important aspect. The National Electrical Code provides specific guidelines for sizing disconnects based on the type of load and the application. National Electrical Code Section 430 covers motor circuits, and National Electrical Code Section 440 covers air conditioning and refrigeration equipment. For general-purpose circuits, National Electrical Code Section 210 provides guidance. These codes specify minimum ampacity ratings and other requirements to ensure safety and reliability. Fourthly, sizing for continuous loads should be considered. If the load is considered continuous, meaning it operates for 3 hours or more at a time, the National Electrical Code requires the disconnect to be rated for 125% of the continuous load current. This rating accounts for the potential heat buildup and prevents the disconnect from being overloaded. For example, if a circuit has a continuous load of 20 amps, the disconnect should be rated for at least 25 amps. Fifthly, accounting for motor load should be taken into account. Motor circuits require special consideration because motors can draw significantly higher current during startup than during normal operation. This is known as the inrush current or locked rotor current. The disconnect must be rated to handle this inrush current without tripping or being damaged. The National Electrical Code provides tables that specify the minimum disconnect ratings for various motor horsepower and voltage ratings. These tables take into account the motor's locked rotor current. Sixthly, selecting the appropriate disconnect type is an important step. Disconnects are available in various types, including fused and non-fused switches, circuit breakers, and motor circuit protectors. Fused disconnects provide both disconnection and overcurrent protection. They use fuses to protect the circuit from overloads and short circuits. Non-fused disconnects only provide disconnection. They rely on separate overcurrent protective devices, such as circuit breakers, to protect the circuit. Circuit breakers offer both disconnection and overcurrent protection in a single device. They can be manually operated or automatically tripped by overcurrent conditions. Motor circuit protectors are specifically designed for motor circuits. They provide overload and short circuit protection and are designed to withstand the high inrush currents associated with motor starting. Seventhly, considering the voltage rating is necessary. The disconnect must be rated for the voltage of the circuit it will serve. Using a disconnect with an inadequate voltage rating can lead to insulation breakdown and electrical arcing, which can be dangerous. Ensure that the disconnect's voltage rating is equal to or greater than the circuit's voltage. Eighthly, factoring in environmental conditions is an important step. The environment in which the disconnect will be installed can also affect its sizing and selection. Disconnects installed in wet, dusty, or corrosive environments must be rated for those conditions. NEMA ratings such as NEMA 3R, 4, and 4X indicate the disconnect suitability for various environmental conditions. NEMA 3R enclosures are rainproof and sleet resistant. NEMA 4 enclosures are watertight and dust-tight. NEMA 4X enclosures are watertight, dust-tight, and corrosion resistant. Ninthly, proper installation and maintenance should be taken into account. Once the disconnect is properly sized and selected, it must be installed and maintained correctly to ensure its continued safe and reliable operation. Follow the manufacturer's instructions for installation and regularly inspect the disconnect for any signs of damage or wear. Tighten connections as needed and replace any damaged components promptly. Tenthly, documenting the calculations and selections is helpful. It is always a good practice to document your disconnect sizing calculations and selections. This documentation can be helpful for future reference and can also be required by local electrical inspectors. Include the load current, the disconnect rating, the type of disconnect, and any applicable National Electrical Code sections. Finally, working with qualified professionals is always important. Sizing disconnects can be complex, especially for motor circuits and other specialized applications. If you are unsure about any aspect of the process, consult with a qualified electrical engineer or electrician. They can help you select the right disconnect for your application and ensure that it is installed and maintained correctly. By following these steps, you can ensure that you are sizing disconnects safely and in compliance with the National Electrical Code. This will help to protect people and equipment from electrical hazards and ensure the reliable operation of electrical systems. Here is an expansion on the recommended practice of including a secondary disconnect for transformers that power machinery, even when not explicitly required by code. Firstly, enhancing safety is a paramount reason. While the primary disconnect provides a means to energize the entire transformer, a secondary disconnect adds an extra layer of safety for personnel working on the connected machinery. By isolating the secondary side, you eliminate the risk of backfeed or accidental energization from the transformer while maintenance or repairs are underway on the machine. This is especially crucial in complex industrial environments where multiple electrical systems are interconnected. Secondly, facilitating maintenance and troubleshooting is important. A secondary disconnect simplifies maintenance and troubleshooting tasks by allowing technicians to isolate the transformer and the machinery it powers. This isolation makes it easier to diagnose and repair faults, replace components, and perform routine maintenance without disrupting the entire electrical system. It also prevents accidental damage to equipment caused by voltage fluctuations or other electrical anomalies during maintenance. Thirdly, enabling load shedding and energy management are further benefits. In situations where energy consumption needs to be reduced or managed, a secondary disconnect can be used to selectively shed loads. By disconnecting the transformer and the machinery it powers, you can reduce the overall energy demand of the facility. This is particularly useful during peak IOs or in response to emergency situations where energy conservation is critical. Fourthly, complying with best practices and industry standards is generally encouraged. While the National Electrical Code may not explicitly require a secondary disconnect in all cases, many industry standards and best practices recommend it as a way to enhance safety and reliability. Organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA, promote the use of secondary disconnects in their guidelines and recommendations. Fifthly, simplifying lockout and tagout procedures is an important consideration. Lockout and tagout, or LOTO, procedures are essential for preventing accidental energization of equipment during maintenance or repairs. A secondary disconnect simplifies LOTO procedures by providing a readily accessible and clearly labeled point of isolation. This makes it easier for authorized personnel to de-energize the equipment and secure it in a safe state before commencing work. Sixthly, minimizing downtime and improving operational efficiency are benefits of secondary disconnects. By providing a quick and easy means of isolating the transformer and the machinery it powers, a secondary disconnect can help minimize downtime and improve overall operational efficiency. This is particularly important in the industries where downtime can result in significant financial losses. Seventhly, accommodating future expansion and modifications is another advantage. As facilities grow and evolve, electrical systems often need to be expanded or modified. A secondary disconnect provides a convenient point of connection for future loads or equipment. This makes it easier to add new machinery or modify existing circuits without disrupting the entire electrical system. Eighthly, enhancing system resilience and fault tolerance is an additional benefit. In the event of a fault on the machinery side, a secondary disconnect can be used to isolate the affected equipment and prevent the fault from propagating to other parts of the electrical system. This enhances system resilience and reduces the risk of widespread damage or disruption. Ninthly, facilitating inspections and testing is important. A secondary disconnect makes it easier to perform routine inspections and testing of the transformer and the machinery it powers. By isolating the equipment, inspectors and technicians can safely conduct tests and measurements without the risk of electrical shock or damage to equipment. Tenthly, providing peace of mind and reducing liability is a final important consideration. By investing in a secondary disconnect, facility owners and operators demonstrate a commitment to safety and reliability. This can provide peace of mind and reduce the risk of liability in the event of an accident or equipment failure. In summary, while the National Electrical Code may not always mandate a secondary disconnect for transformers powering machinery, it is generally considered a best practice to include one. A secondary disconnect enhances safety, simplifies maintenance, facilitates load shedding, complies with industry standards, simplifies local procedures, minimizes downtime, accommodates future expansion, enhances system resilience, facilitates inspections, and provides peace of mind. By considering these factors, you can make an informed decision about whether or not to include a secondary disconnect in your transformer installation.